Hi, I'm Shashi. So I'm going to discuss a very famous interview question, which is finding diameter of a binary tree. So we'll be given a binary tree and we have to find the length of diameter of that binary tree. So let's first talk about that what is diameter. So diameter is nothing but the longest path between any two nodes in that binary tree. For example, if you talk about this binary tree, so the diameter will be this path, right? Because this is the longest path between any two nodes for this given tree, and the length of the diameter will be 1 2 3 4 5 6. So here our answer will be 6, right? And again, the diameter may or may not pass through the root node. Like in this example, the diameter is passing through the root node. But if you talk about this binary tree, then the diameter will be this, right? Because this is the longest path between any two nodes for this given binary tree. And this is not passing through the root node, right? And the length of this diameter will be 8. So basically we have to write a function that will return the length of the diameter, and in that function the input will be the root of that tree, so that with the help of root we can go to the any node of that binary tree. So let's talk that how we can solve this problem. So if we observe this carefully, we'll find that the diameter is nothing but the simply the sum of left height plus the sum of right height plus 1 for a given node. So if we talk about this binary tree, so this is simply 1 plus height of left subtree, which is 2 in this case, plus the height of right subtree. So okay, so if I'm at the root node 1, then the height of this left subtree is 2 and the height of this right subtree is 3, right? And 1 is for the root node. So 1 plus 2 plus 3 is 6, which is the length of the diameter, right? So I mean, this is the case when the diameter is passing through the root node. In some cases, as I have told, that diameter may or may not pass through the root node. In that case, again, I mean, if you talk about this node, so for this node the left height is 3 and the right height is 4 plus 1 is for this node. So this is 8, which is the length of this diameter. So if we say like this, diameter is nothing but the maximum value of this expression for any node. I mean, so diameter will pass through a node, right? And if the diameter is passing through that node, so for that node the value of this expression will be maximum. Like if you talk about, I mean, this node, so the left height for this node would be 1 and the right height for this node would be 5 and plus 1 for this node, so it's 7. So like, I mean, if you talk about the longest path passing through this node, then that path would be this, right? And this path contains 7 nodes. Okay, so basically we have to find the maximum value of this expression for every node. That will be our answer. So I think logic is very clear, that we just need to go to every node and we just need to find the the height of left subtree and the height of right subtree, and then we have to calculate this expression. And if this expression is maximum than the current maximum value of this expression, then we will update that answer, right? Okay, so this is how we will solve this problem. So let's talk about the solution, that how we can implement that logic. So let's discuss the first approach of implementing that logic. So basically we have already discussed that the answer will be simply the maximum value of this expression, 1 plus the height of left subtree plus the height of right subtree, right? So we have to find this thing, and to do that I have written a function that will calculate the length of the diameter of a given binary tree. So okay, so this is the function. The input is the root node, and our answer will be stored in a global variable answer. Initially it will be initialized with 0 value, and this function is returning nothing. It is of y type. So the base case is if the root is null, then okay, it will simply return nothing. I mean, I'll return simply from that portion. Okay, so the base case is if the root is null, then I'll return from that thing, right? I'll do nothing after that. And as our logic, I mean, we need to find the height of left subtree, and to do that I'm calling another function height, which will calculate the height of left subtree, right? And I'm storing that value in LH. So we have another height function which will calculate the height of a given tree, and to find the height of left subtree we need to pass the left pointer of that node, right? So I hope you understand that how height function works. So I have written the code of height function here. So as you know, height is nothing but the maximum of height of left subtree and right subtree plus 1, right? And the base case is if the root is null, then the height will be 0. So I'm returning 0. And to calculate the left height, I can use the same height function, and I'll call the left pointer of that node in the height function so that it will calculate the height of left subtree, and I'm storing that value in LH. Similarly, in RH we are storing the height of left subtree. Okay, and as we know, the height is nothing but simply the 1 plus maximum of height of left subtree and right subtree. Okay, so this is how height function works. I hope you know this function. I mean, if you don't know this function, then it won't be easy for us to analyze the diameter of this tree. So I'm assuming that you already know that what is height function is. Okay, so this is the height function which I'll be using inside this function to calculate the height of left subtree or to height of right subtree, because we have to use that height to calculate the diameter. So yeah, I mean, it's easy to understand, and the complexity of this function is O big O of n, right? Because I'm assuming that the number of nodes in this binary tree is n, and this function will go to every node. So this function will be called n times. That's why the time complexity of this height function is big O of n. Okay, and if you talk about the space complexity of this function, then it will be big O of h. So h is the height of this binary tree. I mean, if the tree is a skew tree, then the height could be equal to n. In that case, h, I mean, this would be big O of n. But if the height is log n, then the space complexity will be big O of log n. So I mean, the space complexity will be big O of h, because in recursion we are using the stack, and the maximum size of a stack will be the height of this binary tree. Okay, so let's come to the main function, which is the diameter function. So we are calculating the height of left subtree using the height function and storing that value in LH. Similarly, we are calculating the height of right subtree and we are storing that value in the RH. And as we know, the answer, the length of the diameter is nothing but the maximum value of this expression for every node. So I am updating my answer variable here. So it is answer equal to max of answer, maximum of answer till now, plus the expression for this node, on which we are currently, right? So if the diameter is passing through that node, then the value of this expression will be maximum for that node. So I'm updating the answer here. Yeah, so this is we are doing for one node, and to do the same thing for every node, I need to go to the every node of the binary tree. So we are simply using the pre-order traversal to go to the every node. So as we know, in pre-order we just go to the root node, and then we go to the left subtree, and then we go to the right subtree. So similarly, I'm calling the same function to go to every node of left subtree, and I'm calling the same function passing the right node of that node, because it will go to every node of the right subtree, right? So basically we need to go to every node and find the value of this expression, and the maximum value of this expression will be our answer. So I think it's not that tough to understand this function. I'm simply going to each node and I'm calculating the expression of this value, and I'm storing the maximum value of this expression in this global variable. Okay, so let's talk about the time and space complexity of this function. So this function will be called n times because it is going to the every node of the binary tree. And at every node we are calling another function, height function, which will again take big O of n time. So basically we are calling this function n times, and in each call we are calling another function which is taking big O of n time. So the time complexity will be big O of n square. And similarly the space complexity of this function will be big O of h. So this is the implementation of approach 1. Can we optimize it? Can we make it in big O of n? Let's see. Okay, so let me explain that how this function is working. So when this function will be called with the root node, okay, so let's say we are at the root node when the pointer of root node is the pointer of 1, and for this node the left height will be 1 and the right height would be 5. So the value of this expression would be 1 plus 5, which is 7, and the current value of answer is 0, so the value of answer would be updated to 7. Okay, so after that we will call this function in the left side for the left subtree. So now the function will be called to the pointer to this node, right? And for this node the left height is 0, the right height is 0, so the value of that expression would be 1 plus 0 plus 0. So it is less than the value of current value of answer, so answer won't be updated, right? So it is a leaf node, so it won't go, so basically at this node also the function would be called in the left side and the function would be called in the right side, but the left child is null, so the function would be returned from here, and the right side is also null, so the function would be returned from here, right? Yeah, so basically our recursion would come from here, and now it will go to the right subtree, so we'll be at the 5. So when we will be at the 5, the value of left height would be 3, because the height of this subtree is 3 and the height of right subtree is 4. So the value of this expression would be 8, which is greater than the current value of answer. So now our answer would be updated to 8. Okay. Similarly, now the function will go to this pointer at 12, right? And again at the 12 we will calculate the left height and we'll calculate the right height. So basically this function will go to the every node, and for every node we'll be calculating the value of left height and right height, but the value of this expression won't be more than 8 for any case. Let's say if we talk about this node, so for 7 the left height is 0 and the right height is 3, so the value of this expression would be 4. So I mean this is not greater than the current value of answer, so answer won't be updated, right? So this is how this is how this function is calculating the length of the diameter of that tree. So let's discuss the second approach, which is the optimized approach than the first approach, right? So let's first think that this is the same function, this is the same old function that was working in n square time and we go of h cross h space, right? So just think that how we can optimize this function, how we can make to big O of n, right? So if we observe very carefully, then we can find that we are calling this height function again and again, and it's taking big O of n time to calculate the height of the left subtree or right subtree, right? So if we can do this work in big O of n, so if we can perform this task in big O of 1 in constant time, then the complexity of our function would become big O of n. And how we can do that? So let's say if we have the height of every node stored somewhere, let's say in a map. So let's say we have a hash map, which is unordered map in C++. By the way, I'm using C++ for the implementation, but if you use Java or Python, then the logic is same and the syntax is just a little bit different. I hope you can understand the syntax as well. Okay, so we have a hash map, and in hash map we can search, delete or insert a key value pair in constant time, right? So this hash map is storing the height of every node. So the key is the pointer to the node and the value is the height of that node. For example, if we talk about this tree, so the height for this node is 3, right? But for the height of this node would be 1, because for this subtree the height is only 1. For this subtree the height is 2. So basically in the map the entries will be like this. The pointer to the key will be the pointer to a node and the value will be the height of that subtree. So this is the pointer to node 1 and its height is 3, and this is the pointer to node 2 and its height is 1, and this is the pointer to node 3 and the height is 2. Similarly for this node the height would be 1. So this is how the information would be stored in our hash map, and using this thing we can simply calculate the height of a node in constant time, right? So because we have the reference to that node, pointer to that node, so we can simply find the height of that node in constant time. So what we do, instead of calling this function, I'll simply write like this, map of root dot left, because we have to find the height of left subtree. So instead of calling this function, I'll do this thing, and this will work in constant time. So now the cost of this operation has become so now this expression will work in constant time. So the function would work in big O of n. Similarly for the right, to calculate the height of right subtree, I'll use map of root dot right. Again it will work in constant time. Okay, yeah, and other steps are the same steps. We have just changed this step, so now these two steps are working in constant time because we are using hash map here. The first thing is that how we can store the height of every node in the hash map. To do that, it's very easy. We can do that using the same height function. So what I'll do, I'll call this height function before calling this diameter function, right? So this height function would return the height of that tree, that binary tree, and it will store the height in the hash map for every node in that process itself, in that function itself. So what it's doing, I'm simply so basically if the root is null, then return 0. This is the base case. If we have so this is simply the memoization. If we know DP, then if you know the dynamic programming, so what we do, if we have to calculate the value of same thing again and again, then we cache that value, we store that value in a map or array or something. So we basically memorize the value of that function, and if that function is being called again and again, then we can use the value of that function which has been calculated before from that storage, from that hash map or something, right? So here I'm using the hash map to store the value of a function for a given node, that is the height of that subtree, right? So here I'm simply finding the height of root. If it is already in the map, that means we have already calculated the height of that node, so we don't need to calculate the height for that node again. So I'll simply return the value stored in the map. So sorry, here it would be map. Okay, yeah, so we are not calculating the same thing again and again. And if it has been not calculated before, then I'll simply calculate the height of that node like this. The height is nothing but 1 plus max of height of left subtree and height of right subtree. And to calculate the height of left subtree, we can call the same recursive function for the left node and for the right node, right? So this expression will give us the height of that subtree having root, this root node, right? And we are storing that height in this hash map for that node. Okay, and after that we are returning that value. So basically we are memoizing the height of every node. So I hope you know the concept of memoization, right? This is related to dynamic programming, but it can be used anywhere, right? Yeah, so using this thing, basically I'll call the height function from the root, and while calling this function, it will store the height of every node in the hash map so that we can find the height of any node in constant time. So now our function will work in big O of n. If you talk about the space complexity, it will be big O of h for this recursive diameter function, plus we are using this hash map to store the height of every node. It will take big O of n space, right? Because we are using the hash map. So the space is simply big O of n, and the time is again big O of n. This is more optimized than the previous solution, but we can make it more optimized if we can remove this hash map. If we can do in the constant space, or the space required for the stack in the recursion call, that is fine. If we don't use any extra space, that would be great. So let's think about that, how we can solve this problem without using this hash map in big O of n time complexity. Okay, so let's talk about the most optimized approach, which is the third approach. And again, the logic is same. The diameter is nothing but the maximum value of this expression for any node. So if you see the height function very carefully, then we can easily find that in the height function only we find the height of left subtree and we find the height of right subtree, and then we return the maximum value of left height or right height plus 1, right? So this is what we do in the height function. And again, we calculate the height of left subtree and right subtree for every node, and this is what required in calculating the diameter. So we can use this. So basically we can calculate the maximum value of this expression in this height function only. So let's say our answer is stored in the global variable answer. So we just need to update the value of our answer variable here, max of answer, or 1 plus left height plus right height. I mean, now we are simply done. So we are simply calling the height function, and in the height function itself we are updating the value of this expression, right? Because we have already the height of left subtree and the height of right subtree, and we just need these two values to calculate this expression, right? So I mean, and we are updating the value of answer for that given node. So I mean, using the height function only, we can calculate the length of diameter. So this is very simple function. This is the height function, and we are just adding this extra line which will calculate the diameter, the length of diameter for that ray. So the difference between height and diameter is the height is 1 plus max of LH or RH, but the diameter is 1 plus left height plus right height. I mean, here we are taking both the heights, right? But here we are just taking one of the left height or right height. So this is how we can calculate the diameter in time n, because the height function works in n, big O of n, and again the space is big O of h because we are using recursion. So basically this recursive function will use a stack to store the function calls, and the maximum number of function at a given time would be equal to the height of the tree. So that's why the space would be big O of h. So this is the most optimized version, and you can find these codes on the given link in the comment section.